And we got 6.1 here, factoring out the greatest common factor. And remember, we talked a little bit about this last time, but factoring is kind of the opposite of distribution. It's not the opposite of multiplication necessarily, it's the opposite of distribution. So we're looking at, I guess, multiplication with many terms, not just one. Because then the opposite of multiplication is just division, okay? So, yeah, that's what this is saying. Factoring is the reverse of multiplication or division. To factor polynomials, to find an equivalent expression that is the product of the polynomials. And usually, I guess, what you've seen if you've taken any 950 or 920 classes here is that what you would end up doing is you end up factoring out the greatest common factor, which by itself is a monomial. So if you've been in 950 or 920, I think maybe even a little bit of 900, then you've done some of this before at least. Just we're gonna add a little bit to it, okay? Actually, to demonstrate this, okay? So it's like saying, right, if you're to distribute like 3 multiplied by the quantity x plus 4. Okay, so you'd say, well, I'm going to distribute the 3 to the x and get 3x, and then I'll distribute the 3 to the 4 to get positive 12 like this. What we're saying now is instead of starting with that distribution, you're going to start with what you ended up with, 3x plus 12, and then we say, hey, we want you to factor this. All right, well, then you'd factor out a common factor with both terms, which is 3, and then what you'd end up left with is just x plus 4 like this. Okay, so like I said, it's just backwards. It's the reverse. All right, when factoring a polynomial, you look for common factors in every term, and then we reverse. Yeah, it's the reverse of the distributive law. It's kind of the same thing right there, but we're looking for common factors for every one of the terms, no matter if it's a binomial, a trinomial, or any kind of polynomial. We're looking, especially in this particular lesson, we're looking for greatest common factors. So we want common factors with every term. Yeah, and then it can be factored. If it can be factored further, just make sure you do. We're going to use prime factorization for this. Okay, so that's like a factor tree, which I think we've seen a little bit of. Now, the other thing you'll need to be aware of is if the leading coefficient, and these are usually already written for us in descending order. If the leading coefficient is negative, we generally factor out a negative as a common factor. Okay. Now, well, what if the term is positive? Then it's like we're saying that term would be double negative, okay? So to think about this, right, if you got like a negative x squared and then plus x, even like this. So the leading coefficient here is this negative 1. So we'd say we're going to factor out this negative 1. But how do you factor out a negative 1 from what is this positive 1 term? Well, this goes back to what we learned pretty much the first week of classes. Sometimes mathematics is just forcing it to be what you want to be. And the truth is that instead of looking at this as positive 1, you could have just made it a negative or minus a negative 1 like this. Okay, now you have a negative 1 to pull out of there. All right, so if you understand that you can just change that like that, which is okay. Like, I didn't change anything like the value of this. Let me rewrite the whole thing though. So negative 1x squared minus negative 1x like this. I didn't really change the value of the expression. I just changed the way that it looked. That's all I did. Okay, and if you could just understand that, then I would kind of hope that factoring kind of, I hope it becomes kind of easy. All right, so the greatest common factoring and factoring by grouping. I don't think we see a lot of factoring by grouping in this lesson, but certainly a lot of greatest common factor kind of stuff. Right? And like I said, that's where we're looking at factoring out a monomial, which is a common factor of all of the terms. Okay, so just so we can remember what a term is. So like if I had that x squared plus 2x minus 1, x squared is its own term, 2x is its own term, and negative 1 is its own term. Okay, so we're looking for any common factors for all three terms, and then seeing if we can pull that out so that it would look like you would need distribution after that. Okay. So find the greatest common factor of the numerical coefficients, then look at your variables, and then pull out anything that's common. Okay. Product of the factors from steps 1 and 2 is the greatest common factor of the monomials. Yep. So it's going to say, well, what is the greatest common factor, and then actually factor it out. So as far as I remember, this homework has like 2 questions per problem. All right, so here's what we're going to do. To factor these out, we're going to make a factor tree like I was talking about. We'll include the variables, by the way. And then we'll circle the prime numbers, and, well, I guess the variables too. But then we're going to make that a list, okay, of all of the factors, in which, of course, since it's multiplying by the letters, the variables, we include those in the list. We don't know how to factor the variables because we don't know what value they represent. Okay, so then in a row, we'll write the factors for each term. Any factors that are common are factored out because they are part of the greatest common factor, that's GCF. Multiply the greatest common factor by the remains of the original expression. When all factors are used, a 1 will remain. This is talking about the terms that were already there. Okay, if you factor everything out of a term, put a phantom 1, well, it would be a phantom 1 there anyways, but we're going to have to show that to hold the spot for that term. If the leading coefficient is negative, we usually factor out the negative as part of the, yeah, we already talked about that, okay? So I would think that a lot of this wouldn't make sense right now because we haven't done this, I think. But like I said, if you've taken 950 or 920, you've seen this process already, okay? There we go, here's a nice example. Now, like I said, we gotta look at each term. This is a trinomial, we gotta look at all 3 terms. And the term I'm going to start with here is the 6x to the power 5, okay? 6x to the power 5. Now, what I'd like to do is find the prime factorization of 6, okay? So I know that 6 would, I could split it up into its factors of 2 and 3, both of which are prime. Okay, so like I said, I circle those, okay? So now my 6x to the power 5, instead of showing it as 6x to the power 5, I got 2 times 3. Those are the prime factors of 6. But then I also have 5 of these x's. 1, 2, 3, 4, and 5. Okay? Well, why did I have to expand that out? Because I want to see all of them for now. And it's highly likely that eventually you'll get enough experience with this where you're like, I don't need to expand this. And you can find your own little shortcuts here, okay? But for now, I'm going to show it. The next term that we see in this trinomial is 10x to the power 4, okay? So I'm going to factor that as well, the 10. I think I got some space here because 10 only factors into 2 prime numbers. That would be 2 and 5, both of which are prime. Okay, so my 10 now is instead of 10, it's 2 times 5. And once again, instead of showing this as x to the power of 4, I'm going to show all 4 x's being multiplied. That's all we're doing, breaking everything down into what is its prime factors. Again, right now I haven't changed the value of anything. All I've done is change the way that it looks, which is a very crucial math skill if you can just do that. If I haven't said this before, like you can do calculus and anything beyond that too, okay? So then we got 2x to the power of 3. Now 2 is already prime, so I don't have to change that into its prime factors. It's just 2. But then it's got 3 x's multiplied together, okay? Now you'll notice that I put a little space right here, and that's on purpose for now because, I mean, I kind of know what's coming, but if you didn't do that, that'd be fine. You can move the x's closer. Some students, that little space there kind of bothers them. You don't have to have it there, okay? Well, we want to factor out this greatest common factor, but we have to know what the greatest common factor is, okay? So this is where we start looking for matches for all 3 terms. And whatever we see that is matching for all 3 terms will result in our greatest common factor here, okay? So what I notice is that we got some 2's that match right there. All 3 terms have 2's that match, so I'm going to put that down as a greatest common factor. Okay? Now I'm going to show this a couple ways. Hopefully we have enough time to do that, but we'll see. Now I got this group of x's right here. I know I didn't circle those very well, but they're all common for all 3 terms. Same with this other group of x's right there. There's another x, And as it turns out, there's another group of 3x's right there. Okay, so to simplify my greatest common factor, I'm just going to show it as 2x to the power of 3, okay? So our original expression, 6x to the power of 5 plus 10x to the power of 4 plus 2x to the power of 3, I just factored out from all of those terms a 2x to the power of 3. So now we look at all three terms and we see what was left over. That will be going on the inside here, okay? So the first term, which was 6x to the power of 5, that's what I put in red right here. All that I have left from that is the 3 and then the 2x's. So I will write that in as 3x to the power of 2. All right, now I look to the purple term, that was the 10x to the power of 4. And what do I got left from there? 5 and an x. All right, well, where the 10x to the power of 4 was, now I got a positive 5 x, yep. Now this, we kind of covered this on that last slide, but notice how all the terms from the 2x to the power of 3, that's my final term here. They were all taken. That's where I need this phantom 1 right there, okay? So all that I have left from the 2x to the power of 3 would just be a phantom 1. Sorry, that's kind of small, but that right there is the answer, okay? Now, the other thing, like I said before, is this original expression right here that they had, this trinomial. Now, we factored out the 2x to the power of 3. These have the same exact value. It just looks different, okay? So this means that if you took this 2x to the power of 3 and distributed it into the parentheses here, you'd get the same exact expression that we had started with. And that, I'm just pointing out that I didn't change any values. All I did was change the way they look. I mean, I'm talking about the overall value of the expression, right? Like, I definitely changed the way that it looks, though. But that's what it's asking us to do right there. Now, I said I'd show this a different way. So let's look at our original expression here. So there's our original expression. So what did I do with the 6x to the power of 5? Well, remember, I then changed it into 2 times 3 times x times x times x times x times x. Right there, like that. And then the 10x to the power of 4 was 2 times 5 times x times x times x times x. Now, you'll notice that I end up doing the same thing. It's just shown in a different way. And that's okay if you do it. It's really up to you, right? And yeah, we got the plus signs between those. Okay, so again, this is just showing that we didn't change any of the values. All we did is change the way that it looks. And then what we see from here is that each of these has a 2 and 3 x's from each of the 3 terms that I can pull out, right? So to rewrite this, and most students don't show it this way, but you can. So that'd be like saying you got 2x to the power of 3 times the 3x to the power of 2. That was the first term. The second term, right, because these are all separated by addition, would have also had 2x to the power of 3 times 5x. Times, there we go. And then we also had the 2x to the power of 3, right? It's like we kind of took these 2x to the power of 3s and just yanked them out, and that's what we end up with right here, okay? So, and then you see what's left over, right? 3x to the power of 2, 5x, and then the, well, maybe it's good to see that phantom 1 right there. Around here, then it's, like I said, it's kind of like you're yanking out this 2x to the power of 3 from all 3 terms, because it's common. And so if once we pull this out and put it right there, then it's like saying, well, it used to be part of all 3 of them, but we just wanted to see it on the outside right here. All right, well, it is possible for these to have 2 variables at a time like we see here. But the process remains the same, and while you could do it the second way that I did that last one, I'm gonna continue to do it the first way. In my opinion, I think it's just a little bit more organized, okay, but you can decide for yourself. All right, so I'm gonna start with this 4x y to the power of 2. I guess I'll do this one in red, all right? So 4x y to the power of 2, that's a 2. And I'm going to take my 4, I'm going to split it up into its prime factors of 2 and 2. Right? So that'd be like 2 times x times y times y. I think we've discussed this in the last module. Be careful, this x, there's not two of those x's. Remember, there's a phantom 1 there, okay? Some students make that mistake where, oh, there's a power of 2, but it applies to both these bases. No, it's just the y. Okay, so x, y, y. All right, now we got that's the first term. The middle term here, 16x, y to the power of 3. So let's put that down here. 16 x, y to the power of 3. And then 16, I guess we got to break this one up. I need a little bit more space. I'm going to do it up here in the top right. So there's 16. I guess I'd split that up into 4 and 4. Some people say 8 and 2. That's fine. But 2 and 2, so 4 is also 2 and 2. 4 2s. Okay, so the 16, just the 16 part of that becomes 2 times 2 times 2 times 2. Then, like I said, we got an x and 3 y's in this one. Now we got the last term right there, oh, and that's a negative. Come on, there we go. Negative 8x, x to the power of 2, y to the power of 2, all right? Now that's not the leading coefficient. If it was, then I would be looking to yank out a negative out of each of the terms. And there's a reason for that, which if we don't cover in this class, then you'll definitely cover in 1010. But I'm going to look at this as negative 8x to the power of 2, y to the power of 2. All right? So negative 8x to the power of 2, y to the power of 2. I guess I can do that 8 below. So 8 splits up into 4 and 2. 2 is prime, and then 4 is 2 and 2. Okay, so that ends up being, and again, I want to show the negative. I'm going to show it with the negative 1 right there. I'm putting it in parentheses, although you wouldn't necessarily have to, but that's now 2 times 2 times 2 times x times y times y. Okay? Now that I have all three terms broken down into their prime factors or just factors, I guess I should have mentioned this before, but remember, factoring is multiplication, right? If you look at a factor of values, you're looking at multiplication. So that's what we're looking at here. And, well, now we're ready then for our greatest common factor. Greatest common factor, GCF. All right, well, let's see if we can find some on this. So I got a 2 here, a 2 here, and then I got this 2 right there. So there's a 2 in common right off the bat, but also this other 2 right here. Now, if you want to be a smart aleck, you can go here and then highlight that 2 like that. And if you do that, you'll drive a math person crazy. I don't really care, so whatever. I'm going to keep it like this just to show. It doesn't matter which 2's we're matching up right here, but once they are matched, then they become part of the greatest common factor, which means they've been pulled out. Okay, so some students are like, well, you still got this 2 right here that's common with this 2. Remember, it has to be common for all 3 of the terms, all right? And they have to be separate for all 3 terms, okay? So we got those 2's, and then we got this x with this one and this one, all right? So there's also an x that's common, and then there's also this y with this one, okay? So there's also a y and another y, it looks like. This one, and this one. See, I skipped this y right there. However you keep track of these is really up to you, but 2 times 2 is 4, x is x, and then y to the power of 2. So I just yanked out from the original expression a 4x y to the power of 2. Okay, so that means from the original expression, I just pulled this out. It's kind of close. See if I can do this so it doesn't start mixing there. Okay, so I just pulled out a 4x y to the power of 2, and I'm just looking for at each of the 3 terms to see what was left over. Okay, so I look at my red term, and nothing was left over. Okay, so that's where we need a phantom 1 to hold that place value. Okay. Yeah, and then I go to the purple one, and what was left over there? I got a 2 and a y right there, so that's a positive 2, and then the y. And then in green, I got, remember the negative one there, then the 2 and the x. So negative 1 times 2 is negative 2, and then the x. Thank you, there we go. Let's fix that there. The other two, don't forget, take a little bit more time than I'm doing to make sure, or keep track of them better than what I did. That's why I also don't recommend skipping the values like I did there. But 2 times 2 there in purple, yeah, it should have been a 4 there, thank you. All right, so just to clarify the answer here, because it kind of got a little jumbled there. It's this one, okay? So, and well, the last part of the question here is just that it asks for the actual greatest common factor. That's this 4xy to the power of 2 on the video, okay? But I'm going to look for the greatest common factor for all 3 of these terms. It's just got a lot of letters. Well, the first term and the third term have lots of letters, but whatever, okay? So I'm going to look at each of them separately. My 12, m to the power of 2, n to the power of 3, p to the power of 6. That's a lot, but I can split that up, right? So 12, I'm going to split up into its prime factors. That'd be 3 and 4 for me. You could use 6 and 2, but I'm going to use now 2 and 2, okay? Same prime factors no matter what. And so what do we got here? We got 3 times 2 times 2, and then we got 2 m's, 3 n's, and then 6 p's. Dang it. A lot of p's there. 1, 2, 3, 4, 5, 6. There we go. So that was our first term. Now the middle term I'll do in purple. That's a 33m to the power of 5, and then n to the power of 7. I wish they could have used smaller numbers. Whatever. I'll just one in the top right, the 33. Well, that's just 3 and 11. Oh, that's not too bad. They're both prime. So that ends up being 3 times 11. And then 5 m's. 1, 2, 3, 4, 5. And then 7 n's. I'll try to use some technology to make this faster. There we go. Maybe not as pretty though. All right, and then we got that last term. Again, that's a negative 39 because the minus sign, negative 39. M to the power of 4, N, P to the power of 9er. All right, so what about negative 39? Let's split that up, find its prime factors. Well, just 39 really. We'll deal with the negative one here. So I would say 3 and 13 on that one. That should work. All right, so 3 times 13. Now let's do that one. We got 3 times 13. I already see that 3 in common, and I'll even throw in that negative 1 to account for the negative, right? Then we got 4 m's, 1, 2, 3, 4, an n, and then, oh man, 9 p's. Dang it. 1, 2, 3. This may help us. That's good. All right, so I am looking for my greatest common factor on this, okay? And although today we've seen some factoring by grouping, I really shouldn't expect something like this, especially with terms that have 3 different variables in them, okay? So I'm just looking for anything that's in common. That will be my greatest common factor. That will answer one question. Like I said before on the homework, it will ask for the full expression too, okay? So what's my greatest common factor? I got 3, like I said before, there's the 3's that are in common. So it is a part of the greatest common factor. I don't see any 2's or 11's or 13's or even negative 1's that are common either, so that's no good. Oh, we do have m's though. See if I can narrow this down. This m with this one and then this one. Okay, so we'll put in an m as a common factor. In fact, there's another m, right? These ones right here. Oh, looks like we got some n's as well. So this n with this one and this one. So that's all the n's we got that are common. Remember, it has to be common for all 3 of the terms. So even though there's lots of p's right here and here, there's none in the middle term that would make that common. So I'm just going to take my time here and just double check. I don't see any more m's in this one, even though these 2 do. I don't see any more n's in this one, but these 2 do. And then we already went over the p. So I'm not seeing any other common factors. So our greatest common factor in this one is just 3m to the power of 2n. Okay, now that would be one of the answers, but we got to compare this with what we had in the beginning, right? So we're going to put everything that was left over in parentheses, term by term, and we'll put the greatest common factor out there in the front, 3m to the power of 2n. Okay, but like I said before, this first part right here, this would be one of the answers that you'll have to put into Canvas, okay? So the first term that we have in red there, I got 2 times 2, which would be 4. And then we got the 2 n's, that'd be n to the power of 2. And we still got all 6 p's right there, so that's p to the power of 6. That's my first term. Then I go to the second term. In purple, I got an 11. That's positive 11. And then we got 1, 2, 3 m's there, so m to the power of 3. And then n's, 1, 2, 3, 4, 5, 6 n's. So that's n to the power of 6. And that's all of the purple term that was left over. And then the green term, right? We got the 13 and the negative 1, that would be negative 13. And then I got the 2 m's, that's m to the power of 2. And then all 9 p's, there, so that's p to the power of 9. Yep, I don't see anything else. So that appears to be our second answer for this one. But the process will be the same for this one. So I'm going to look at each of the 3 terms. So again, I would look at the negative 10x to the power of 6 on its own, negative 10x to the power of 6. And then I would look to factor out the values. Now, once again, we got that negative 10. That's our leading coefficient, which means on this one, I definitely want to factor out this negative 1, okay? So I would just be looking at 10. That'd be 2 and 5. I guess we've seen that one already. So it'd be negative 1 times 2 times 5. And then we got 6 x's. Oh, man. 1, 2, 3. Use some technology. There we go. There's 6 x's. Now, since the leading term, and we did talk about this, since the leading term is negative, I'm going to force each of the terms to have a negative, whether it is showing as negative or not in the original expression. So that's a negative term right there, but this one right here is a positive 2. I'm going to force that 2 to be negative so I can yank out a negative from that term. Okay, so it's just going to happen like we saw. Remember that adding a positive is the same thing as subtracting a negative. So that's what we're going to be seeing on that, okay? So my next term, though, negative 14x to the power of 2. So let's factor that one out. Negative 14, x to the power of 4. There we go. All right, so 14, and again, this has got the negative, so I'm going to show the negative 1 there. But my 14 is going to factor out into 7 and 2. Now, for convenience, you could put the 2 first, but I forgot to do that, so I'm going to just pretend like we didn't notice that. So 7 times 2, that'd be the 14. We got the negative taken care of with the negative 1, and then we should have 4 x's. 1, 2, 3, 4 x's. Okay, so that's the middle term. And then, like I said, that last term right there, since the leading coefficient is negative, I'm going to look at this 2x to the power of 3 and force the 2 to be negative, which means really it just ends up being a double negative on that, okay? So, yeah, that's right now it's positive 2x to the power of 3. Now, I'm going to show you that it is the same, because it's like saying you're going to take negative 1 and multiply it by negative 2, okay? Well, why the crap would you do that? It's because I want to force this negative 1 out of all 3 terms, okay? And the only way that I could have done that with the positive is to make both these values negative. You can do that? Yeah. I didn't change it. I didn't change the value of 2. It's still, if you multiply those, you still get a value of 2. It's just showing a little different. Okay, and then we got the 3x's being multiplied. Okay, now that we have that, we are ready to find our greatest common factor. By the way, I didn't use a factor tree with 2 just because it's already prime. Okay. All right, so what do we see here? Well, I do have the negative ones that are common, right? So I'm going to yank those out as a part of the greatest common factor. Oh, look at this. So right now, it's kind of showing the 2's as separate right here. So I want to see them all as positive 2's. I'm I'm actually gonna go back in, and instead of showing this as just -2, I'm gonna use another -1 on that, okay? Really more for, I guess you'd call it semantic purposes, but -1, and then there's a 2, okay? Because I want to show that the 2's all match. If I keep that there as a -2, sometimes that causes confusion. So there's a 2, there's a 2, there's a 2, okay? And they are all common factors of each of the 3 terms. And then we also have an x, an x, and an x. For all 3 terms there, there's the 1, and then we got another 1 there, and then another 1 right here. There's an x. Okay, so if we multiply this all out, -1 times 2 is -2, and then x times x times x, I can do better 3. That's a little better. All right, so that all came from all 3 of the terms that we had originally started with. So that's a -2x to the power of 3 in the beginning, or in front of the parentheses, which again, if we distribute it into all 3 terms, we should end up with the same exact expression that we started out with. But what do I got left from the original -10x to the power of 6? I got a 5, and then I got these 3 x's multiplied, all multiplied. So it ends up being a positive 5x to the power of 3, okay? And again, making this positive will be pretty crucial. And then for the middle term, which we have in purple, I got a positive 7 and an x, which means that would come out as positive 7x. And then our final term here in green, yeah, there's only the -1 that was left, so I'm going to show that as -1, okay? And now it's all factored out. That should be it. Now, you got to be careful because when you look at an expression like this, there's only 2 terms. You got the b times b minus 4 term, and then you got the -8 times b minus 4 term right there. 2 terms. So technically this is a binomial right now. Even though within each term there's some subtraction, we would still consider this a factor of its own, okay? And what I just said there is a crucial part of this, because once we start factoring these by hand, whether we do it in this class or you do it in 1010 is kind of obsolete. It's just as long as you understand that this is a term and then this is a term. And so, again, I'm just stressing this out. B minus 4 in parentheses is a factor. But notice that it's a factor for both terms, right there, which means just like we had seen before, it's a common factor right now. I'll try to highlight this. B minus 4 action right here. I'll try to make it a little bit more pretty. This B minus 4. Hopefully that's better. And then this B minus 4, they're already common factors right there that I can just pull out. Okay, so I'm gonna put them over here on the left. B minus 4. Okay. Now you'd have to do kind of what we're looking at before. Is you look at the 2 terms and you see what's left of the 2 terms. Well, for the first term you have this b right here. That's all that's left, so it stays. For the second term, you got a -8 there. That's all that was left, and so you put it there. Okay. This is more like what you're going to be seeing, but to get to this point in the future, you're going to have to take at least one step. Okay. Generally speaking, but this is actually what we're looking for on this problem. And if you switch the order of this, I'll show that. You can switch the order of these. Try to use some technology to make it faster, though. Like this. It's the same thing, it's just shown in a different order. That doesn't matter, and Canvas doesn't even care. But it means the same thing, and this is our final answer, both of them. So it is possible to factor out we call this by itself a binomial. And that's okay if you do that, because now if you start using, if you like FOIL, that's fine, but I just like distribution. If you want to distribute whatever you have here into this, or even back here, then you'd end up with the same expression either way.